Thank you for the introduction and good afternoon, everyone. So in this presentation, I will discuss the wafer level experimental characterization of some MEMS structures that we have designed to operate as gyroscopes and that were fabricated in a commercial MEMS process by STMicroelectronics. So nowadays, inertial navigation is one of the most demanding applications for inertial sensors, and this is in terms of performance is especially true for gyroscopes. However, as engineers, as sensor designers, not only we have to focus on the maximization of performances of our devices, but we also have to keep an eye on the economic sustainability of the devices that we want to fabricate. So the point is, we have to make sure that our sensors can be produced in large volumes and with very large production yields, so to comply with market requirements. One way to do this might be to, for example, develop custom fabrication processes. This has been done in recent years for example, micro glass-blown hemispherical resonator gyroscopes that you can see in this picture. However, developing a custom process is a huge and time-consuming effort. Not only you have to come up with the optimization of the process itself, you have also to come up with packaging options and standardization of process and so on. So one more immediate solution might be to resort to already available fabrication processes, mass market fabrication processes that we already know are capable of large production yields. The point is we have to verify that these standard processes are compatible with high-end specifications. And this is why in this work we have designed MEMS structures to be operated as whole-angle gyroscopes. These are very promising candidates to meet the specifications of inertial navigation applications, and this is due to the fact that they are capable of directly measuring absolute angles, so orientation angles, which is a huge advantage in navigation with respect to traditional rate gyroscopes, for which you need numerical integration, which also affects noise and offset and brings to a fast increase in positioning errors. For a structure to be used, for a gyroscope to be used in whole angle mode, the two specifications we need to fulfill are very high quality factor, the higher the better, and highly symmetric structures, so basically mode matching condition between the two resonant modes of the device. In order to check this, we have designed dual Foucault pendulum structures, and we have fabricated them in a standard mass market MEMS process, the TELMA process by STMicroelectronics, which is used daily for the production of millions of devices. The process is based on a 30-micron epitaxial polysilicon structural layer, and we have limited the design area to 3.5 millimeters squared so that we can fit about 1,200 devices on a single 8-inch wafer, so to comply with large production volume requirements. All of the wafers that we have produced were processed as in a standard production chain by STMicroelectronics, except for the last bonding capping passage, which was performed at pressures below 50 microbars, so an unusual value for the process, and this was done to achieve basically the largest possible Q factors for these structures. So in the next few slides, I will be discussing first the design and basically the geometric structure that we have designed, and then I will move on to the wafer level characterization of the devices. So the device is called a dual Foucault pendulum. It consists of two nested masses that are coupled with tuning fork springs, which results in the two anti-phase modes that you can see the animations down there. Ideally, these two modes should be degenerate, so they should lie at the same frequency, and this resonance frequency was chosen to be 29 kilohertz. The value is chosen to be outside of the audio bandwidth, so that in principle the gyroscope is able to reject acoustic audio disturbances during the operation. Actuation and sensing of these structures are performed by comb finger electrodes, which are nested within some decoupling shuttles in the structures, and we chose to use comb finger electrodes to avoid the use of parallel plates, which are typically associated to a squeezed film damping effect, which degrades the quality factor in MEMS structures. And the other reason is that we wanted to keep actuation and sensing the most linear as possible. For the same reasons, we have implemented electrostatic tuning electrodes in this structure as tapered comb fingers. This geometry was proposed in 1998, but as far as I'm aware, it was never used in an actual gyroscope for tuning of the two modes. The advantage is basically that this geometry allows an electrostatic force to be generated linearly proportional, linearly dependent on the displacement of the structure, and this implements what is sometimes called a perfect electrostatic anti-spring. So I will now move on to the wafer level characterization. All of the measurements that I'm going to show have been performed at wafer level with a probe station system that you can see in this picture. We have characterized the quality factors and resonance frequencies of the devices, and we put particular focus on the matching, so on the relative mismatch of these parameters. So in order to characterize the quality factors, we have performed ring down tests. We have applied chirp excitations to the two modes of the devices separately, and we measured ring down response. We have fitted, we have extracted the envelopes of this ring down response, and we have fitted them with exponential decays whose time constant is inversely proportional to the quality factor of the mode. And we have found values of the quality factor in the 300K range, which is close to the theoretical thermoelastic limit for these structures, which is 400K. We have also found that for this specific sample, the anisodamping, so basically the relative mismatch of the quality factors, is 1.5%, which is a really good number for the operation of these devices as whole angle gyroscopes, as it sets a locking threshold of about 125 millibps. So this is the characterization of the resonance frequencies. As I said, we are particularly interested in the mismatch of the two frequencies, since these devices are expected to be mode matched. You can see a heat map of the frequency mismatch that we have measured on some modules around the wafer in this slide. And interestingly, we have found 40 Hertz average systematic mismatch between the two modes, even though the devices were designed to be symmetric, perfectly symmetric along the two axes. We think that this systematic asymmetry might be due to some actually systematic asymmetry in the module layout, so basically for the presence of the pad cavity, which makes the module itself asymmetric with respect to the X and Y directions, or to the asymmetric layout of the interconnections of the device. Around this average value, however, we have found that the distribution of the frequency mismatches is approximately Gaussian with a standard deviation of 13 Hertz, which can be ascribed to local etching non-uniformities, as you cannot see a definite trend on the wafer. We have also verified that among about 80 devices that we have tested, the worst case mismatch is plus minus 35 Hertz. And the point now is to tune this residual mismatch down to 0, since we want the structures to be mode matched. And this is why we tested the electrostatic tuning by applying a DC voltage, actually a set of different DC voltages to the Y mode of the devices, which was found to be systematically above the X mode. This is the result. As you can see, as we sweep the DC bias voltage of the electrodes, we get a change in the frequency of the Y-axis, and we have demonstrated a 53 Hertz tuning range at a reasonable tuning bias value of 25 volts. We also managed to reach a quasi-matching condition by manual tuning of the two modes, in which we have reduced the initial 26 Hertz mode split to below 400 millihertz. Please note that this was obtained by manual tuning. We're expected to reach even lower values in operation, since this has to be done by an automatic mode matching circuit, so basically by an algorithmic procedure. And finally, we have also verified that tuning is linear with the square tuning voltage as expected from the theoretical model. So to wrap up and to conclude, we have demonstrated that the TELMA process, standard mass market process by STMicroelectronics, is compatible with the requirements of structures to be operated as whole angle gyroscopes. So basically we managed to obtain devices with a very high quality factor in the 300K range and with a quite good symmetry between the two modes, and we demonstrated that even though we cannot achieve perfect mode-matched structures on a whole wafer, we are able to tune the mismatch, the residual mismatch down to basically 0, which is what we are required to do for the operation of the device. So this is the end of the presentation, but please stay tuned because we are currently developing a control system, an electronic control system for these devices to be operated as whole angle gyroscopes, and we have demonstrated actual angle measurement capabilities. So hopefully in the next few weeks and months, we will come up with some news about that. So thank you for your attention, and of course, if you have any questions, they'll be